Hello everyone. In this video I will be doing 6 questions, organic questions of the September 2022 question paper of the NET, National Eligibility Test. So I will be doing only the organic questions. So let's start with the question number 16. The question says, given below are the bond dissociation energy in kilojoules per mole values. Based on the data, the correct statement about the following. So you are having one keto form tautomer and the enol tautomer, and they are given this bond energies and asking which is more stable, A is more stable or B is more stable. If A is more stable, it will be stable by how much energy? If B is more stable, it will be stable by how much energy? Now very clearly A is more stable. You know that um, A is keto form, in this one is enol, and that's why keto is the major product because it is more stable. And the idea is this: I remember values in calories much more better than the joules value what they have given. So when carbon oxygen single bond is there, the energy, the bond energy is 69 kilocalories per mole, whereas carbon single bond is there, the bond energy is 71 kilocalories per mole. So by 2 kilocalories per mole, carbon bond is more stable. But when you come to carbon oxygen double bond and carbon double bond, so carbon single bond was around 69, right? And then when the pi bond comes, you have to add another 61, I think 61 kilocalories per mole further, okay? But when you add carbon oxygen double bond, you have to add more. You have to add something like 79 kilocalories per mole. So the pi bond is actually much more stable than your sigma bond in carbonyl. Whereas here, of course, pi bond is weaker than your sigma bond. So what happens here is, it's not just pi bond, it's not just covalent bond. The pi bond is also ionic character, and there is a charge interaction, and therefore pi bond is more stable, and therefore ketone is way more stable than your alkene, right? We have to now find out how much stability is there. So this is very simple question. It will be class 11th question. So bond dissociation energy of one tautomer, so they have given this. So there is one carbon oxygen double bond. The things what they have given is, they have given you bond energy of carbon oxygen double bond, carbon double bond, carbon hydrogen single bond, carbon oxygen single bond, oxygen hydrogen single bond, things like that. So carbon oxygen double bond, we have to calculate, you have to add 1 plus 2 into Cc, because 2 carbon bonds are there, plus 6 into Ch, so equals to 1 carbon oxygen is minus 760, carbon is 360, minus 360, so 2 into minus 360, this, you get answer as minus 400 kilojoules per mole. So minus means when these bonds were formed, this much energy was released. So it is more stable than single identity, it is more stable by 400 kilojoules. When you take enol form, then what is there? One carbon double bond is there, so you have to take one carbon double bond. Then what is there? One carbon oxygen single bond is there, so one carbon oxygen single bond is there. One carbon single bond is there, so that carbon single bond is there. One OH single bond is there, one OH single bond, and then uh, two right 5 CH bonds are there. So that comes to minus 3930 kilojoules per mole. I think I have done one mistake. This will not 400, this is 4000, okay? This is 4000, right? So now bond dissociation energy, now you see here, this is minus 4000, this is minus 3930. That means keto form has released how much more energy? It has released minus 1000 minus 930, so 70, right? So minus 70, so it has released 70 joules more energy. So therefore A is more stable by than B by 70 joules, right? Yeah, so just is that the negative value tells about the how much more stable is there. So the energy is minus 70 kilojoules per mole, right? I should have written this, I don't know how I missed it. Anyway, question number 17. I will go once again through it. You can read as I go through it. Yeah, moving to the next question, question number 17. The major product in the following reaction is, so you are having this molecule where you have allylic alcohol, not allylic alcohol, yeah, is alcohol is there, and then one alkene group is there, and you are reacting with benzaldehyde in presence of AlCl3. What's the product formed, right? So AlCl3, is a Lewis acid. So its octet is not complete, so it will act as powerful electrophile. So what happens is, it will act as electrophile, and the most nucleophilic electrons will go and donate. So there are three kinds of electrons here. One is lone pair, one is pi bond, and there are sigma bonds. Now sigma bond electrons are least nucleophilic, then comes pi, then lone pair are most. So of course this will go and attack here to get positive charge. Now then this leaves and you get a positive charge. Why it leaves? One thing is because it has become a better leaving group. Oxygen has positive charge. If it leaves, it will become neutral. Apart from that, leaving of this OH leads not to very unstable intermediate. You get a benzylic intermediate. You see here. So benzylic, because phenyl ring is there, this goes and pumps electron here. You get positive charge like that. You get lot of stability. Now what happens is, after this, where is it? Something has gone wrong. It has disappeared. But basically, benzaldehyde will go and attack here. So, right, you are having benzaldehyde. So this benzaldehyde would go and attack on this positive charge. So benzaldehyde, what is the formula? PH, CHO, right? CHO, C double bond O and H. Now we again know that oxygen has lone pair of electron. Lone pair is more nucleophilic than your pi bond. So this goes and attacks here, and then what you get here is this species. And once you get this species, this becomes very electrophilic because oxygen is having positive charge, and pi bond which can easily migrate. So it's a very large antibonding molecular orbital. So this pi bond goes and donates electron, you get like this. And then what happens when OH left the AlCl3? Al has negative value charge. Okay, when OH was there with the AlCl3, you are having negative charge on the aluminum. So once this leaves, you get a negative charge here. Now this negative charge goes and attacks here, and you are getting this Cl. So the answer is option number D, right? So this was a bit odd because Cl minus is not a powerful nucleophile, it's a quite weak nucleophile. But please understand, you are having a positive charge here. So when you are having positive charge here, it's like vacant p orbital. That is the most electrophilic thing you can think about. Okay, it's more electrophilic than pi star. It is definitely much more electrophilic than your sigma star. And therefore, though positive charge is though Cl minus is a weak nucleophile, because positive charge is there, this Cl minus which has come out of the species goes and attacks here, and you get this product. Okay, answer is option number D. Once again, I'll go through it. I somehow missed drawing one of the steps. Read every sentence what I have written. A lot of details are there in this. Okay. So what I have talked about is, there were two species. AlCl3 could have been attacked by benzaldehyde also, or could have been attacked by this alcohol also. But this oxygen was sp2 hybridized, whereas this oxygen is sp3 hybridized. Now sp2 hybridized means it has more S character than sp3, right? sp2 has how much? 33% S character, because out of 3, one of them is S. Whereas in sp3 it's only 25%. Now we know that S orbital has more penetrative effect than p orbital. So this here S character is only 25%, here S character is 33%. So it has more S. S is closer towards nucleus, more penetrative than p orbital. So because it is closer towards nucleus, electrons are more stabilized here, more closer, that means more attraction, more energy is released. So here electrons are more stable than here, and therefore this energy is lower, this energy is higher. So for nucleophilicity we need higher energy. Those orbitals which has higher energy will be more nucleophilic than those orbitals which has lower energy, and therefore This lone pair is what attacks first AlCl3 and not the PHCHO. Okay. Moving on. Moving on to question number 18. The major product formed in the following reaction is. So this is like you have to know it. If you don't know, it's tough to know. So it's basically you are having ketonic group and you are having ester group and you are reducing it. Any given day, ketone is much more susceptible to reduction than ester. So ester will not reduce, ketone will reduce. And this catalyst you have to know R-BNF, when it reduces, it's a asymmetric catalyst. Okay, so it will give you R alcohol. If S-BNF would have reacted, it would give you S alcohol. So the answer is very clearly C, because this will not be affected. This only you have to find out if it is R or not. So you can look here, just put the hydrogen away from the viewer. So we know in CIP rule the lowest priority should be away from the viewer, and we know that hydrogen has lowest priority. Look at this carbon. So this is the chiral carbon. We have to give priority according to atomic number. So oxygen has highest priority, then comes carbon, but this carbon gets more priority than this carbon because this carbon is connected to another carbon which is connected to another carbon, whereas this carbon is connected to another carbon but then connected to oxygen. Here it is connected to carbon. So that's why this is second, this is third. So you can see that it is going clockwise. Clock rotates like this, or you can also see R is written like that. So this is R. So this is the answer, option number C. Yeah, question number 19. The reaction with positive entropy of activation delta S, activation energy, that is the symbol of activation energy. Okay, this one is or R. So what do you do here is basically you have to find out what is the tension state. The entropy, you know, entropy is degree of disorderliness. So if you see tension state is more disoriented or the reactants are more disoriented, so you have to look at all the reactants, and so you have to know the mechanism also, how many reactants are involved. So in this one, the first one, let us look. So this is a ester. First step is of course addition of this acid and it becomes like that, and then it is a SN2 reaction. It's a SN2 reaction. This goes and attacks and you get this species, and then this lone pair comes down and the leaving group leaves. Now this is the tension state what we are talking about. So understand, for this tension state we needed two reactants, 1 plus 1. So two reactant had of course much more degree of disorderliness than both of them coming together and you are giving such a constrained strained species. So here the delta S is positive and not sorry, delta S is negative here, because negative positive means more disorderliness, it is less disorderliness. So therefore delta S tension state is activation is negative here. Okay, moving on here. So now you see this reaction. The reaction is this: you are attacking H2O. Now this is tertiary butyl. There is no way water will be able to go and attack inside. It is a SN1 reaction. It's a tertiary. So tertiary, you know, tertiary always goes through SN1 mechanism. So first the leaving group leaves. You get a carbocation. And then water goes and attacks. So here what happens? First it leaves, and before it becomes carbocation, there is this tension state what we are talking about. Now imagine what happens in a tension state. First, this bond has become longer. So of course it is much more disorderliness. It is more free to move. So therefore here delta S is positive because it is more disorderly, the tension state. Third reaction is this one. So here of course it's as simple as this. It undergoes by radical mechanism. This leaves here, this leaves here. Tension state, this long bond becomes longer. So more freedom to move. So again delta S is positive here. So I'll go from top again, you can read it. Question number 20. The major product formed in the following reaction is. So you are having this molecule and reacting with BF3 etherate, dietherate, okay. So BF3 is a Lewis acid, so you never get BF3 separately. You will always react, you will see it is with THF or diethyl ether, right? And what's the product formed? So first thing is it will react with BF3 and something has to leave very clearly. So lone pair would have attacked from this oxygen also and this oxygen also. Why we are doing this is because this OH has better chances of leaving, because if this leaves you get a benzylic carbocation, and benzylic carbocation you see here, this oxygen, this also would have attacked but it does not yield to any product, so we are not talking about it. It attacks BF3 and then BF3 leaves, you are getting the same reactant again. But here what happens is once this attacks BF3 you are getting a positive charge, then once this leaves you are getting a positive charge, this stabilizes and you are getting this, right? Now, but why will it leave? It will not leave unless it gets some anchimeric assistance. It needs to form it, somebody has to help it. So what happens is this OH is there, no, it pumps electrons in the antibonding molecular orbital of CH. Now CH is exactly anti-periplanar to this, so this goes and attacks here on the anti-bonding. So you know anti-bonding exactly 180 degrees to this. This is the bonding. If this is the bonding molecular orbital, how will be the anti-bonding? Sorry, I should have drawn bonding better. Let me draw the bonding better. So bonding, you know, this lobe will be much bigger and this will be much smaller. How the anti-bonding looks like? Anti-bonding looks like ulta. So anti-bonding looks like this. This is small and this is very big. So this goes and attacks, gives the electrons in the anti-bonding molecular orbital, and this leaves. So you can see very clearly the anti-bonding is below this pH. So H comes below, pushes the pH on top, and you're getting this and you're getting this. So now you can see here tertiary butyl is above the plane because H is here in the axial bond. Tertiary butyl is above the plane, equatorial. So because H is below the plane, tertiary butyl is above the plane. So you have to draw it towards the viewer. CO is anyway planar. This pH is above the plane, H is below the plane. So you have to draw pH above the plane. You are getting this product. This is answer number C. Let's do the last question for the video. The major product formed in the following reaction is. So you are having this and you are having bromo and you are acting with methanol. So allylic bromides are beautiful electrophiles, very powerful electrophile. One simple reason is CBr bond is very weak. So what happens? CBr bond is very long, very weak. So imagine if carbon-carbon bond was there. So carbon-carbon bond is strong, it is small. So what happens when the two atomic orbitals interact, when two carbon interact, because they are giving lot of stability, so bonding is having much lower energy, anti-bonding is having much higher energy. Whereas if you make it to CBr, now Br is weaker, CBr bond is weaker, so stabilization is not much, you see, stabilization is not much, so little amount of stabilization is there. So for nucleophile we need higher energy, but for electrophile we need lower energy, right? So because this bond is having much lesser energy, I'm so sorry, electrophile means anti-bonding, just one sec, let me delete this circle. Yeah, anti-bonding means electrophile means anti-bonding does not have the electrons are here. So the electrons from nucleophile will attack on the anti-bonding molecular orbital. So you can see that anti-bonding molecular orbital has lower energy in this than this, and therefore for a better nucleophile we need higher energy. So if I compare between CC bond and CBr bond will be more nucleophilic, but they are not nucleophilic. Sigma bond rarely pumps electron. But if I look at electrophilicity, clearly this bond is much more electrophilic than this one because it has lower energy, so it is easy to accept electrons here. And which will accept electron, carbon or bromine? So of course between carbon and bromine, bromine is more electronegative, so electrons are more stable on bromine than carbon. So carbon has higher energy, bromine has lower energy. So when they combine and they form bonding molecular orbital and anti-bonding molecular orbital, anti-bonding molecular orbital is closer towards the energy of carbon, and the bonding molecular orbital of bromine is close of the molecular orbital closer towards bromine. So when the nucleophile attacks, it attacks on the carbon, not on the bromine. Okay, I hope I made a lot of sense. uh, so that's what happens here. That's what happens here. And apart from that, when this bromine leaves, bromine is leaving, you get a transition state. Now what is the effect of this allylic group? Because this bromine is leaving, so you get a transition state where your sigma star is there. Okay, sigma star of CBr and nucleophilic attack, this is there. This is parallel to the pi bond, and therefore this overlaps and stabilizes the transition state. This is most interesting, and therefore allylic undergoes SN2 reactions beautifully. It also undergoes SN1 reaction beautifully. Why? Because if it undergoes by SN1 mechanism, then you get a carbocation. This carbocation will have vacant p orbital, and that p orbital overlaps with the pi bond. Here the transition state, this bond is overlapping with the pi bond. So very clearly it is going SN1 reaction, SN2 reaction, sorry. Now what happens? Now clearly if it is SN2 reaction, it is nucleophilic attack. It is not about charge-charge interaction. So though oxygen has negative charge, sulfur is much larger in size and has lone pair of electron. It's a softer nucleophile. Is soft means nothing. It's all about orbital interaction. So this is a bigger antibonding lobe, and this also has much bigger lobe than oxygen with negative charge. Therefore this goes and attacks here, this leaves, and you're getting this product, right? So that's it for today, this video. Thank you. So I will go from top to bottom one, sorry. Oh sorry, we did this. Oh, we did this, I'm sorry. Read through it. I have written everything what I said is written here. Maybe it will be written more elaborately. Okay, thank you so very much.